working? Yes. Cool. So in this talk, I want you to ask this core question. How do we represent language? So in order to understand it, I want to tell you some usage of natural language processing in today's products and how it's becoming more and more important. And I give now some examples where NLP is having a big impact. So one of the most popular and most successful examples is text classification. So for example, spam filtering, the removal of spammy emails from your inbox is of course very valuable. Also things like sentiment analysis and language identification are also good examples for text classification. Machine translation is also a really good example of how language can be used for practical tasks. Over the years, machine translation has improved a lot, and the algorithms that are used have changed a lot. Going from dictionaries and heuristics, we moved to statistical translation combined with a huge amount of labeled and unlabeled text. Only since around 2016, we are using approaches based on neural networks, which considerably improved the quality of the automated translations. Natural language processing also can be combined with computer vision models to generate text, for example, and for image captioning. In this example, it's giving descriptions of these images, and it's really useful for making image searchable and helps people with vision problems to better understand and navigate on the internet. But we can also use the same models, for example, to generate music. So this is one example from OpenAI called MuseNet, which generates MIDI wave files. Really sounds like so it really generates some coherent music. It's an example of it generating some video game music. Also speech to text and text to speech are getting better and used more and more, especially now that devices as smart speakers and voice assistants are becoming very popular. Natural language processing is very important for these techniques. They use machine learning models to convert speech data into text and also map text to audio waveforms. And there are much more tasks in the field of natural language processing, like information retrieval, text generation, summarization, etc., etc. So in order to understand how we can improve these technologies further, we must first understand this core question. How are we using language? And how do we represent language in our systems and models? One of the first and most popular ways to represent text is the back of words approach. So imagine you tokenize a sentence like "Where's my package?" Into words and put them all in a bag. This is just the back of words approach. Back of words has some serious advantages. Really simple and really fast, and leads to very efficient and scalable implementations. But it also has some very serious disadvantages, which makes it perform worse than alternative approaches. So for example, tokenization is very arbitrary. So why do we even split sentences up into words using white space? It's really sensitive to spelling errors. So one error can make a system not detect at all what you're talking about. And it also doesn't take word order into account because it's just a set of words. And also each word is completely unique. So given two words that may be similar to each other, when it's a new word, it has to learn it completely from scratch. So in this example, how word order becomes a problem is pretty obvious. So dog bites a man, in this case, isn't equal to man bites a dog, but based on the back of words, word approach, those are the same. And it also doesn't take word similarity into account. So for example, the distance or the similarity between walking or walk and laughing is the same as the similarity between laugh and laughing, just from this representation. So one way of improving the order of words is called the n-gram approach. So in this example, we create, instead of 1 grams, we create bigrams of text to represent a sentence. So you see now that it includes information about the local ordering of words, and the model can also be trained that is more accurate. It can discriminate between sentences which are do different ordering. So the very obvious advantage is that it takes this order into account, but and it can also be used in other domains like analyzing DNA sequences and extracting features from images. The older approach for image recognition. But some serious disadvantage is that it creates a problem of data sparsity. In practice, this means you need a very big data set to cover a lot of your language and a lot of your combinations of words. And also each n-gram is still unique, so it doesn't take any similarity structure of the word into account, and it also doesn't need any learn any global structure. With n-grams, data sparsity is a real problem. You can really see here in this table. So what you see here is the amount of combinations that can occur when you scale up the number of n-grams in your features. So with just unigrams is 10 to the power of 4, with bigrams 10 to the power of 8, etc. So combinations of words are also less likely to appear in this data set, and you need an even more and more bigger data set. So for example, in Google Translate, before it used neural approach, it needed something like 200 million words of parallel training data to learn the relation between two languages. So how can we take order into account? There are nowadays quite some alternatives in deep learning to tackle this problem. So for example, LSTM, recurrent neural network, goes through the words one step, one word by one word, and learns from that a certain representation. As a convolutional neural network combines local features to build up more abstract way of representing text. An important lesson of these models is that instead of manually extracting features, we have to offload that to the model. So instead of manually learning things from data or extracting things from your sentence, we need to put that more into the model, so the model learns to represent documents and sentences. And the model becomes more powerful from that. So if you have enough data, there are quite a few models that can learn from scratch the relation between a sentence and what you want to predict. But you need sometimes hundreds of thousands, millions of labeled examples to do this pretty well. So what if you don't have this amount of labeled data? Some of the somewhat older ideas to tackle this problem are called word embeddings, which is also sometimes referred by the algorithm word2vec. So the key idea here is we can use a large amount of available data that's available on the internet. And then we design a task to learn representations from this data and use it then later for other tasks. Sometimes to still keep in mind is that these representations are still not contextual. Each word learns a fixed representation regardless of the place in the document. So one of the algorithms to do this is called CBOW, continuous back of words. What it does is, given a short context of a sentence, it predicts a nearby word. So, for example, the next word in a sentence. And during optimizing this task, which is not at all what you want to learn, but during optimizing this task, it learns to learn vectors or representations for these words. And the nice thing is that these word embeddings can then be used for new tasks. So it helps really on if you have a small data set compared to other approaches like the back of words approach. So question for you. Can you complete this sentence for me? Allemaal? Yeah? Great. So you are an example of a language model. So the idea of a language model is similar to the CBOW algorithm. Given an ordered sequence of words, we predict the next word. So in this case, the man is walking, we predict down. The man is walking down, we predict the next word, the, etc., etc. So the nice thing is that we also can use this model to generate text. For example, in Gmail, there's this functionality called auto-reply or smart reply, and it can give answers to emails in an automated way. But we can also use language models to come up with, for example, grammar and style fixes in your documents. And this is an example of Microsoft Word recently launching this feature. So language models are very powerful to generate text. But as a side effect, they also learn to represent this language in a self-supervised way. And they also create contextual representations only by learning this language modeling task. So here comes the aha moment, I would say. So we use this language model to learn to represent text. And by that, we come up with more accurate models and results for other tasks. So here's how this works. We first learn a representation of text using language modeling. Then we fine-tune a model on a downstream task, like classification or question answering. And you then, because of this, you need much fewer examples, labeled examples, to achieve the same accuracy, which it means much less time spent, much less money spent in your case. So some examples of models that work like this are called Elmo and UNFIT and BERT. And so this is BERT. It's one of the most well-known models. It's based on an attention-based transformer model. It's a bit different in that compared to other language models, it doesn't come up with the next word, but it clears out some words at the middle of a sentence. And BERT leads to state-of-the-art results when using it to train and to fine-tune on other tasks. The E? I'm not sure of the symbols, but those are basically. I think it's just a feature at the place in the sentence. So at this part, it has a certain vector representation for this token embedding, representation for the whole sentence at this place, and positional embedding. So meaning of where is this token in the document that's used there. So attention, which is also an important part of this model. Here's an example of that. So here's it's translating. It's used for attention-based translating. I'll repeat it once more. You see it translating a French sentence into an English sentence, and you see, for example, je suis. If it's focusing on suis, then and étudiant, then it's translating the A. So if you're translating A, then it has to take into account more of the words. So also another important piece of the models next to the structure of them is how they tokenize sentences. So sentence piece is a library and a method that use byte pair encoding algorithm to come up with an efficient tokenization based on the statistics of your data. So one example here you see to the right, if you have some words like low, lowest, new, newer, wider, then it will automatically, based on the statistics of this, come up with tokens which can represent your data. And it really helps to compress your sentences and to give that tokens to the model. One nice extra thing of this is that we can also use it as a reversible method. So we can tokenize some sentence again and then untokenize it again to come up with the same sentence. And that's really useful for example, machine translation, where we predict tokens and then want to convert it to the original sentence again. On the GLUE benchmark, which is a very well-known benchmark, BERT-based models have the most accurate results, which you can see here, and they are on top of the leaderboard. But only humans are still better than all these models for most of the tasks. Well, all this progress and good results is pretty exciting, I think. We also have still a couple of challenges. A thing that is that these models can also be used for by bad actors for malicious usage. So, for example, OpenAI recently made a language model called GPT, and they said, yeah, we don't want to release it because we think there will be a malicious use of this technology. So we will release just a much smaller model which doesn't get the same results as the big model, and we just tell the community with the technical paper to tell them what it is about. But in the media, it was picked up like, for example, Wired, that the AI text generator that's too dangerous to make public. I find it very funny. And another disadvantage is speed. Big models like BERT need a huge amount of GPU memory and training time. So they, at the moment, they can only use or trained mostly on infrastructure that's only there for Google. So TPU, big TPU clusters, basically. They are also too big to run on a mobile phone. so you cannot use them there, and you can also currently not really include them into a low latency service. So those are really slow and big models. And attention-based models also don't really scale to longer documents. So it has quadratic time complexity, which means if you try to generate really big documents based on the attention, it will get slower and slower, and at some point it doesn't scale as well anymore. So lots of R&D is still needed there. Another challenge, I would say, is what are we going to do with bias in data? So as we know, just training on public data sets is going to lead to bias. For in this example, it's related to a profession. So Turkish doesn't have any gender in the language. So if we use a language which doesn't have any gender and translate it to English, then the most statistical, according to this model, thing will come up. So it will say he is a doctor. Now Google added a feature to detect when that is the case. So if you just enter one sentence, it will now generate gender-specific alternatives. Which is a good idea, but it doesn't really scale to longer documents and more alternatives. And also, it's only for genders at the moment. So the conclusion: NLP has had very big advancements in accuracy using modern methods, but it still needs a lot of research to make it practical and more efficient. And the final thing is that we also need to address problems like bias and data and uses by bad actors. So thank you for listening, and please ask a few questions.
Thank you, Daniel. Are there any questions?
So, hey Daniel, how do you use those language NLP technologies at bol.com?
At the moment we don't really use it in production, but we try to investigate in the use of such methods for future use cases. For example, we
Can you repeat the question for?
Oh yeah, of course. What could be those future use cases for bol.com? We use natural language processing a lot at bol.com. For example, in my team, we use it to use it for intent recognition, so to recognize the questions of customer and classify those. But it's also used a lot for search and to analyze conversational data, for chatbots, etc., etc. So the use cases are numerous.
Hi. Oh, yeah, it's pretty loud. Here. What I'm curious about is that there's obviously with natural language is a lot of it is text, but there's more and more voice applications. And have you seen any type of systems that can make use of both, let's say, voice data and text data together? Or do you think that's something that's going to happen soon, or we're still quite a few ways from there?
I think the current method is just to use first speech recognition to convert something to text, and then to use a normal text-based model to come up with the chatbot or whatever, or search or something else. Maybe in the future we will more have a direct use of voice data and to do predictions directly in audio data. But I think at the moment, most practical way is to use a speech recognition system.
Hi, very simple question. Did you see Google's keynote yesterday?
I watched some pieces, but not completely.
Because it was, apart from security and privacy, all about NLP. and they now do offline translation of 79 languages on a mobile phone with an 80 megabyte NLP model, right? So they had a 2 gigabyte model, and they now have an 80 megabyte model which runs offline. So even in airplane mode, it can live translate video, audio, everything. It's
that's
it's
pretty,
really impressive.
Really impressive indeed.
So I was just,
Yeah.
you know, for people that haven't seen it, just go and watch, see the keynote, and you'll be flabbergasted.
Yeah.
It's amazing.
Yeah, really cool.
Let's do one more question. Okay. Daniel, thank you.